We're picking up our discussion here in section 1.3 where we're looking at physical system hierarchy. And the first statement here is complex electronic systems are constructed using the basic building blocks used in simple systems. And this is, we had previously stated that all electronic systems are built from the same basic components. And so in this section we're just going to look at the hierarchy. We're going to look at 6 different building blocks used in electronic systems. And we're going to start out with discrete components, to printed circuit boards, to integrated circuits for ICs, to functional modules, to entire systems on a chip, and this would be of the electronic type, and then entire systems on a chip in the electromechanical type. So first of all, let's look at initial building blocks, and here we have what we're going to refer to as discrete components. And here we see schematic diagrams for resistors, capacitors. Let's see, here's a capacitor here. Here is the resistor, diodes, MOSFETs. Here we have one down in the corner, operational amplifiers, etc. And we have a transistor up here. And these and others are the building blocks of all electronic systems. The next item we'll look at is printed circuit boards. And here we have a printed circuit board here on the right side of the screen. These are components are mounted on thin, non-conductive boards. They are referred to as, and they have 2 common names, printed circuit boards. The acronym is PCB, or sometimes they're referred to as printed wiring assemblies. In that case, it would be PWA. Now, printed circuit boards, they utilize thin copper strips called traces. Sometimes they're referred to as runs. And in this picture here, you can see the copper lines here are actually the copper wires, and we refer to these as runs. They are bonded to the non-conductive base material, which the circuit board is mounted on. They provide electrical connections between components, and the solder joints indicate components mounted on the other side. So you see these little joints here. These are the connection point of components that are probably on the other side of this board. PCBs may have multiple layers. The simple circuits often only use one side of the board. More complex circuits will use both sides and may have multiple layers. Now, I don't know if you can see this clearly on this picture here, but you may see there's some kind of faint copper-looking wires on this circuit board, and these are indicating a layer below the one that you see here. Some may have as many as 20 layers. So circuit boards, especially with, for example, in computer system boards, they may have many, many layers, sometimes as many as 20. And again, here is a picture of a discrete components mounted on a circuit board. And then here is another picture, and here we see there's some capacitors here. We see some resistors and a little IC here. Looks like a diode. This looks like a variable potentiometer, and we have some capacitors here as well. But again, these are discrete components on a printed circuit board. Then we have integrated circuits. Again, building blocks of complex electronic systems. As its name implies, many circuits are integrated together. This is usually done on a thin slice of silicon. Often these are called a chip. They are very small, 0.05 to 0.2 inches wide. Millions of basic components can be etched on these tiny chips. They're functionally similar to their discrete components, except they are many times smaller. And they're connected by tiny traces of material like gold or aluminum. And we'll continue here with IC. The same purpose is served as a printed circuit board, except there is a profound reduction in the size. And over time, if they produce a lot of them, there's also going to be a reduction in the cost. And oftentimes, over time, there's also often reduced failure rates as well. And this has to do with being able to put all of the chips on, or all of the components on a single piece of silicon. It usually stays around the same temperature the entire chip, so that often results in reduced failure rates, because often failure has to do with components that get overheated, they fail. When they're all on one single piece of silicon, that chip usually stays at a uniform temperature and oftentimes will result in longer times without failures. The manufacturing environments for ICs utilize high quality clean rooms. These are Intel as an example. And we have many students from NSC that go to work for Intel down in Portland. Once the chip is produced, it's mounted on larger packages such as those in your text shown on figure 111. And again, here is an example of integrated circuits, and you can see these ICs soldered to a circuit board. And then this is a higher resolution picture of an integrated circuit. This is actually a microprocessor, and you'll notice this is what you typically see in a microprocessor. You don't see this portion that they have opened up in this particular photo. Notice the chip is very small. Remember we said it was only from 0.02 to 0.5 inches in diameter. It is placed in a large case which provides for the pins for interface to a much larger system board. So the actual chip is just this little tiny piece right here, and you'll notice you can see this red portion here is actually all of the wires connecting to the tiny connections on the chip, and then there are other wires that are going out to the many connection points, and these are the many connection points that actually would connect to a system board or motherboard, since this is a microprocessor. And the levels of integration in ICs, we have what we call here SSI for small scale integration, then there is medium, large, and very large, and then over here to the right you can see the number of gates that if it's small scale integration 1 to 10, medium 11 to 99, large scale 100 to 999, and very large scale 1,000 to just under a million, and that would be VLSI. Then functional modules. Electrical engineers combine integrated circuits and discrete components to build functional modules. Now, these can be standalone items like an AM/FM radio or part of a larger systems. Now, the idea of functional modules is that you have a module that can be plugged into another system to give it greater functionality. And just one example I'd mention here is the PCM-CIA devices are examples of functional modules that interface with computers. Now, in this particular situation, you have a computer that has a degree of functionality, and the PCM-CIA card can be plugged in and can give it greater functionality. And there's just all kinds of PCM-CIA devices. They can be used for network interface, global positioning, video capture, and many others as well. But anyway, functional modules designed to not to have, well, sometimes they can have functionality on their own, but typically they're designed to provide additional functionality to an existing system. Then we have systems on a chip, and we're going to be looking at two different types of systems. We're going to look at electronic systems on a chip and then electromechanical systems on a chip. And complete electronic systems are available on integrated circuits such as computers, calculators, and so on. ICs may combine many separate circuits on a single chip. Now here we show a TI-86 calculator. The TI-86 calculator is a complete electronic system unto itself. Usually they will have an IC built into them, and all the functionalities built into an IC is probably inside the box here, maybe about here, and you've got all the connections going to this particular IC, much like we saw in that integrated microprocessor chip. And so we have a fully functioning unit that can do complex calculations and give us a video display as well, and it is a standalone system on a single chip. Then we have electromechanical systems on a chip. Research is underway to provide for the integration of electronic and mechanical systems on a single silicon chip. The machines on these chips include, notice, valves, motors, levers, and gears. Manipulating these micro devices is possible at a molecular and even at the atomic level. This technology is referred to as nanotechnology. And over here to the right we see a picture, and this is a highly magnified nano machine. You can see some gears doing something here, and to get the perspective of the size here, this little creature here is actually a dust mite, and these creatures are only about 250 to 300 microns in length. They are very small, and nanotechnology is a new science. It's in its infancy, really, and there's lots of things that are going to be happening in nanotechnology. Here at North Seattle Community College, we actually have a degree in nanotechnology, and this particular course meets one of the requirements for that degree, since many of these nanotechnology devices incorporate electronic components. Okay, in summary, in section 1.3, we've looked at the hierarchy of electronics components, and we went from the discrete components to printed circuit boards, to integrated circuits for ICs, to functional modules, to complete electronic systems on a chip, and to complete electromechanical systems on a chip.